Okay, in the last lessons, what we had was impulse. Impulse is caused by a force on an object applied for a certain amount of time, and it changes the momentum. Impulse, in fact, is that change in momentum. So if we have a net force on an object, it changes the momentum. Well, an object, we could think of an object as being a collection of a lot of different molecules, right? We don't worry about how all the different molecules interact. So really, if there's no net force on a system of particles, then the momentum is constant. There's no change in momentum. So what we're going to talk about is collisions, which are really simple things where we consider two objects that hit each other. Okay, well, if there's no net external force on that system, no net force pushing on these particles, these objects, then the total momentum of the system will be conserved during this collision. Collision is just an impact, two things hitting each other in this case. And we're going to talk about two different basic primary kinds of collisions. One is an elastic collision. Elastic collision, the total momentum of all the particles in the system is equal to the total after the collision. So we're always going to be talking about before and after some event, some collision in this case. But in elastic collisions, the total kinetic energy is also conserved. So this is something we're going to be talking about later on. Elastic collisions are one class of collisions. Inelastic collisions is pretty much everything else. Okay, still no net external force on the system, so the total momentum is conserved, but the kinetic energy, we can't say anything about that. It could lose kinetic energy, the system could lose kinetic energy, in other words, transfer energy out of the system. You could actually have a thing like an explosion, which is an increase in kinetic energy. So those are not elastic collisions. But today, the big thing we're talking about is perfectly inelastic, sometimes I'll use the term completely inelastic collisions. And perfectly inelastic collisions, yes, the momentum is still conserved, but it's a special case where the objects stick together. This is just a term we have for that. It's an inelastic collision where the objects stick together. Okay, and the way we can do this with these carts is we have Velcro, and if the carts roll into each other and stick together, that is a perfectly or completely inelastic collision. And these are actually, we're starting with this because they're really easy to solve, and it's a good way of introducing how we solve conservation of momentum problems. So we're talking about conservation of momentum, just like we talked about conservation of energy in the past. Conservation of momentum means the total momentum in the system is conserved. So the way I tend to write this is P total equals P total prime. I'll sometimes be talking about the momentum of the center of mass of the system. The momentum of the center of mass of the system is, if we just don't look at these as two separate things, we think of the center of mass of this entire group of particles, and that actually continues with the same momentum if no net external force. And the way we break these down is we do, first of all, a before collision and an after. And we want to represent all the particles in the system before and after. And probably the most important part is to pick a positive direction. So I'm going to have two objects. I'm going to call this the positive direction. Really important because momentum is a vector. And so if you have the directions wrong, it won't work out. As we saw with impulse, right? A ball going in this direction 20 meters per second and then coming back in this direction 20 meters per second was a big change in momentum. Whereas a ball going 20 meters per second and then still going 20 meters per second is zero change in momentum. So really important to get that right. So I'm going to set up something. I'm going to say here comes an object and it has a mass of 5 kilograms and it's going in this direction at 2 meters per second. And then I've got a 1 kilogram ball going in this direction at 1 meter per second. So I know the total momentum before has to equal the total momentum after. So it's pretty easy to figure out. The momentum of this one is 2 times positive 5, which is 10 kilogram meters per second, and I'm going to leave the units out just so it doesn't get too crowded. The momentum of this one is 1 kilogram, mass times velocity, times -1, which is -1 kilogram meters per second. So the total momentum of the system before is 10 plus -1, which is 9 kilogram meters per second. Well, I know the total before has to equal the total after. 9 kilogram meters per second. Well, as I mentioned, if we're talking about a totally or perfectly inelastic collision, these two objects will stick together. I'm just going to draw it as a big blob. 6 kilograms, because we had 5 kilograms and 1 kilogram. That's one big blob of 6 kilograms. If it's two carts stuck together, 6 kilograms. So we know the mass is 6 kilograms. We don't know what the velocity is doing yet, except for this. It's one object. We know the momentum. We know the mass. So this is equal to mv, 6 times v. If we divide by 6, we get a velocity of 1.5 meters per second. This is the way these will generally play out. If you have two objects and you have their velocities and masses, you can figure out what happens afterwards. If you have only part of this information, but you have the information about the after, you can figure out the total here. That's the same as the total here, and work backwards to find a velocity back there. Let's see what happens here. See, this one's going pretty fast, and then collides with this one, and the two of them together end up continuing in this direction. Don't assume a direction for this result. Solve for the direction. The fact that that's positive means this blob is moving in this direction, which really kind of makes sense. This is heavy and moving pretty quick. This is light and not moving that fast in the opposite direction. You would tend to think when they come together, the velocity would tend to be in this direction.